Hello, welcome to everyone in this video. This is lecture number 7 on solid state physics. Today I want to discuss about the Dulong and Petit law, Einstein and Debye theories on specific heat of solid and TQ law, right? You can see this is the syllabus of Calcutta University 6th semester physics honors. This crystal structure, this portion already discussed in previous lectures, and in the second portion, that elementary lattice vibration we discuss for monoatomic, diatomic, acoustic, optical, phonon. And in the last lecture we discussed the qualitative description of phonon spectra in solids. So up to this portion, up to that portion we already discussed, and today we want to discuss that Dulong Petit's law, Einstein device theories, and TQ law. So up to that one, this portion will be discussed today, and in the upcoming session we will be continue on the magnetic property of matter, dielectric property of material, Drove's theory, elementary band theory, and superconductivity. This will be continue in the upcoming session, right? So let's start. You can see Dulong-Petit law says that the specific heat for a solid is constant and with the value is thrice R. R is the gas constant. If you put this value, you will be obtain this 6 calorie per uh, uh, and this is independent temperature. So this law state that Cb, that is the heat capacity at constant volume, is constant, okay, for a solid. But this Dulong-Petit's law, what is the drawback of this law? Because this law failed to explain deviation of heat capacity with temperature. Actually, here the Dulong-Petit's law says that this is the independent on temperature. That is, we low temperature and high temperature both have this constant value. But in the practical view, the Cv is depend on the temperature. So this law is not valid. In the high temperature it is valid, but in low temperature it's not valid. Practically at T tends to 0, heat capacity must be 0, but with this law we can say this is independent of temperature. That means at 0 Kelvin this will be 3R, but practically this is 0. So this is the drawback of this law, and this can be overcome by Einstein and the Debye theory. Okay, so for that you need to know about the classical theory of specific heat of solid. In the classical theory, it's continue at that the crystal content of atom in periodic manner, and each atom is free to vibrate about the equilibrium position. That is the three-dimensional harmonic oscillator. So in the solids, the atom behaves like a three-dimensional oscillator, and imparting the thermal energy increases internal energy in terms of vibrational energy. That is, the vibrational energy is coming from the temperature, heat. A system of n vibrating atoms. So this is 3n independent harmonic oscillator. There are 3n independent harmonic oscillator, and each harmonic oscillator have the natural frequency omega naught. And the energy of 1D harmonic oscillator, a mass m and angular frequency omega naught, is like that. That is the energy p square by 2m, and the potential energy half m omega naught square x square. From Maxwell-Boltzmann's distribution, the average energy of each harmonic oscillator is given by, this is the average energy from the Maxwell distribution. You can see this is the average energy of this oscillator. And if you put this value, that is the energy, this is the energy p square by 2m half m omega naught square x square, in this expression will be obtained this expression. Okay, you do the calculation with this video, you can understand easily. So if you put this value of energy expression and separate out the exponential part, you will be obtain this one, and you can see here that is p square by 2m exponential this one and exponential that one. Separate out p square by 2m, that one, and half m omega square and that one. Just separate out these two portion, and you can see here the integration with respect to x and integration with respect to r gives the same result. These two are cancel out, only obtain the integration with the p and integration with the p present here. Similarly, if in that case integration with respect to p and integration with respect to p are same result, are cancel out, only present in the integration with respect to x here and here. Clear? After that you use the these two formula. This is actually obtained from the gamma formula. You know this well-known gamma formula in the previous semester. You know this e to the power minus ax square x to the power 2 dx. Here actually if you put n, this is n. Here if you put square, because here is the square, so you will obtain this relation. So this is nothing but the gamma function, these two. So if you put this using this gamma function in this integration, you will be obtain this expression, and after calculating you will be obtain kbt. Okay, I think you can do this calculation using this integration formula. Here you can see this is the kbt. So in vibrational three dimensional, so this is 3n epsilon. N is the number of atom, and if n equals to na Avogadro number, this is 3rt. So cv equal to 3r, which satisfy the Dulong and Petit law. So this is satisfy the Dulong Petit law, but the practical cv is not constant with temperature. So this theory, that is the classical theory of the this classical theory of specific heat of solid, is does not satisfy the practical specific heat expression. Okay, so that's why introduce the Einstein specific heat of solids. It take this harmonic oscillator by quantum harmonic oscillator. It replace the classical harmonic oscillator by quantum harmonic oscillator. Here we take the energy value is for classical harmonic oscillator. This energy expression is for classical harmonic oscillator, but Einstein take this as the quantum harmonic oscillator. This is the basic difference from classical to Einstein theory. Okay, there are some certain features on Einstein theory, that is the crystal consists of atom which may be regarded as a identical and independent harmonic oscillator consisting n atom of equal 3n number of one dimensional harmonic oscillator. All oscillator vibrate the same natural frequency, and the oscillator are the quantum oscillator with discrete energy spectrum. In classical oscillator there is continuous energy spectrum, but here the discrete energy spectrum. Any number of oscillator may be present in the same quantum state, and the oscillator distinguishable due to their location and separation. That is, it satisfies the Maxwell-Boltzmann distribution. These are the features taken, or the assumption taken by the Einstein in case of specific heat of solid, in calculation of specific heat of solid, because its expression in the classical theory and Dulong-Petit law does not satisfy in the experimental result of the specific heat, because specific heat changes with temperature, but Dulong-Petit law and the classical theory satisfy that it is constant. So there is some uh, uh, anomaly. Okay, so that is solved by Einstein by this taking this classical quantum oscillator into quantum classical oscillator changes as a quantum oscillator, right? So by Planck quantum theory, you know the energy is n h nu multiplied with the natural number, quantum number, and the harmonic oscillator energy is nothing but n half h nu, right? Or you can change in the angular frequency. Nu is the frequency, and omega naught is the angular frequency. Avogadro, so the average energy is nothing but the summation of this one, because this is a discrete value, so take the summation. For continuous value you need to take integration, in discrete value you need to take summation. Okay, so and then put this value of energy En both side, and after that this is constant, just separate out and then break into the summation form. You know this summation form, just put this value in from 0 to infinite, you will be obtain this expression. And this is nothing but, you can take that is ln of this one is nothing but denominator is like that, and this derivative, so this is equal, no problem. If you take this common into the power x by 2, you will be obtain this one, and this is nothing but this separate out, this you will be obtain this one, and this is the infinite GP series. So the sum of this infinite GP series is a bar divided by 1 minus r. A is 1, 1 minus r means e to the power x. Here multiply the e to the power x. So you will be obtain this one, and this is nothing but, if you interchange these things, okay, this take as a derivative. So if you take the derivative, you will be obtain this one, and if you put this value of x, because x taken as minus h cross omega naught by kbt, you will obtain this one. So there is additional term which is 0 point energy. When temperature tends to 0, this become infinite, so this becomes 0. So at 0 point, that is that 0 temperature, there is a present of this 0 point energy. Okay, so the total energy is multiplied by 3n, you will be obtain this one. So Cv is like that. So this is the Cv in case of Einstein convention. If you take this Einstein convention, you will be obtain this expression. Now comes into the two case, higher temperature and lower temperature. In case of higher temperature, that is this one, cavity is higher than this one, so temperature is very much greater than the Einstein temperature. So if you express this one, this is very high value, so this is low value, so the higher order will be neglected and present only first and second. This one is cancel out, so you'll be obtain this one. So if you put this one, you will be get cavity and Cv equal to this expression. In the above expression, you will be cancel out 3r. So in higher temperature, it's also satisfied Dulong and Petit law, that is classical theory. This is constant, there is no problem. At the lower temperature, if you consider at the lower temperature, this expression will be that one, because this is very low, that means this is very high, so this one can be neglected, you will be obtain this expression. And if you plotted this in the graph, will be like that. But you can see here, this theoretical, that is Einstein theory, gives this curve, but experimental results some deviate at the lower temperature. So Einstein theory gives the matches in the higher temperature region, but there is a anomaly in the lower temperature region. So this is the problem in the Einstein theory. Then comes into account into Debye theory. Okay, so at the very beginning, Dulong-Petit's law gives you the Cv is constant. Then comes into the classical theory, classical oscillator, that is atoms takes into atom take as a classical oscillator. This also gives you the same result at Dulong-Petit's law. Then Einstein take as a quantum oscillator. It satisfy the higher temperature region, but in the lower temperature region there is a deviation from the experimental curve. Then comes into the theory, Debye theory. He take that the Einstein take the all these atoms are independent to one another. This is actually oversimplified, because they in the atom, in the structure, solid structure, the atoms are interlinked, there is an interaction, so they are all are independent. This is not true, this is very oversimplified. So we need to take account the there is a interaction. So Debye I consider the coupled harmonic oscillator. In classical theory, this take as the classical oscillator. In Einstein, take this as the quantum oscillator, but these are the independent. And now Debye take as a coupled harmonic oscillator. Okay, the number of vibration mode or the frequency range is called densities of state. And consider the one-dimensional continuous string of length L, x with the position of the line. Then the displacement from the position at any time will be like that. This is the displacement, that is displacement at any time. So this is the strain, right? And you know this Young's modulus, that is the elastic constant, is nothing but stress by strain. So stress is nothing but force per unit area, here taken as the area is unit, so this is F by E. So consider the element of length delta x, the strain at one end is Ex. So E of x equal to del E del x delta x and this one. Okay. So after calculating this two end string, the force will be like that, and net force of this element is that separation of this one, and force of this element rho delta x del to u del x. And if you equating this two, you will be obtain the one dimension wave equation whose velocity will be like that. So this is the wave equation within the solids, and this gives the solution. Here this lambda n, that is nu n, is like that. So this frequency at the discrete value, this is the frequency at the string or the discrete with the integral value of this one. Now if you take this dn, that is the number of possible mode of vibration in the frequency range d nu, within the solids, the atoms having the frequency interval delta nu, the number of atom will be like 1. And consider the 3D wave equation. If you consider this 3D wave equation with this solution and substitute this value, you will be obtain this expression, and this is gives the possible modes of the vibration. Now if you consider there is spherical symmetry r with radius dr, thickness dr, so the small volume is 4 pi r square dr. The number of modes present in the frequency range nu and nu plus dn will be like that. Since a mode of vibration always determined by the position value, this one, so possible modes of vibration will be like that, 1 by 8 4 pi r square dr. And if you put this value of r, we will obtain this expression. And finally you will be give there is a longitudinal transverse velocity. There is a just taken to vs velocity, but actually practically there is two types of velocity, transverse and longitudinal. Longitudinal means wave propagate along that line, and perpendicular there is two transverse and one longitudinal line, so the velocity expression will be changed like that. Okay. Now, if you take the interatomic distance small compared to the wavelength of elastic wave, the crystal can be regarded as the continuous from the point in view of wave. Okay, so total modes of vibration will be 3n. This is actually Debye approximation. Debye take this approximation. Total number of modes will be 3n, and there nu d, that is Debye frequency, that is the maximum frequency that can propagate to the solid. And if you integrating these things, you will obtain this Debye theory, and the velocity of sound will be, if you obtain, then nu d equal to that hertz. That is the same order there of the distance. So this violate the Debye approximation, that is on continuum, because this is continuum Vt and Vl independent of the wavelength, which not always true. Okay, so this actually the Debye's drawback. And after taking the average energy value in this, if you put this value, will be obtain this expression. You can do this integration just written here, and finally you obtain this expression, and cb will be this one. Okay, so I think you can do this calculation. And for high temperature you will be obtain the same thing. So for high temperature there is no problem. At low temperature you will be obtain these things, and this is to your 4 variation of energy. And you know, in from the Stefan's law of radiation, that is the energy related to this one. So there is a conclusion, that is in case of photon, that is in case of light radiation, the energy relates with the temperature to the power 4 or for all temperature. But in case of phonon, that is the lattice vibration, the energy varies to the 4 at the lower temperature, not in higher temperature. Higher temperature, this is a E is proportional to T, right? So this is the conclusion. And the specific heat will be like that. So at lower temperature Cb rises Tq. This is the Debye Tq theory. That is at very low temperature the specific heat is proportional to Tq. This is called Debye Tq theory. So finally, if you draw this card, that is experimental, this red dot are the experimental result, and Debye actually matches with this experimental result, and in the Einstein will be like that. So Dulong Petit law gives the straight line, that is 3r, which matches in higher temperature. In lower temperature, Einstein deviated some portion, but Debye satisfies this TQ law in the lower portion. So I think clear about all these things we just discuss here. Just calculation, some calculation you need to uh, yourself just do this calculation yourself. I think you can do that. There is a limitation of device theory, that is the device continuum model valid for the long wavelength. Number two, cutoff frequency is assumed to be same for both longitudinal and transverse, but it is not true. And it is theta d, device temperature independent of temperature, but actually is found to vary up to 10% or more. The theory completely ignores interaction among the atom and the contribution of electron in specific heat. So these are these device theories limitation. Okay. There is a question you need to solve, that is the Debye temperature given here. You need to compute the highest vibrational frequency at temperature 30 K. So from here you need you can find this Debye frequency, and just taking the proportionality you can obtain the highest vibrational frequency. And this is your homework. You can do solve this question which are discussed in this lecture. Okay, so solve this question. If there is any doubt, you must comment in the comment box. So this is all about me, and this is my contact detail. You can connect me with this Telegram channel, and this is my YouTube channel details. Go to this channel, you will get different physics related videos, some mathematics. Like this session. If you learn something from this session, share this video your friends, either he or she also get benefit from this video. Subscribe this channel if you need this channel. Those already subscribed, thanks for subscription. Press the bell icon to get notification of upcoming videos. So take care. We'll meet in the next video as soon as possible. Thank you.